In this video, we're going to look at how terminal velocity arises from air resistance. The problem we're going to consider is dropping a ball from a certain height h, and we're going to drop it from rest. And it'll be subjected to air resistance following Stokes' law. And we're going to calculate the velocity, acceleration, position as functions of time. Like before, we do need some calculus. These are the same calculus theorems that we cited in the previous video. The one addition we're going to need is how to do integration by substitution. That is a very important technique, so when you cover it in calculus, make sure you're paying attention because we will be using it. Procedure we're going to follow to solve this problem is just like before. We're going to draw a free body diagram, pick our frame of reference, apply F equals ma, again in the form of F equals m times the derivative of the velocity. We're going to apply our force law, which will be Stokes' law, and again the mathematics we'll be largely calculus. First we have to draw a free body diagram. In this case, we have no normal forces because the ball is in the air. We have no surfaces it's in contact with. Again, no tensional forces and no friction. The only forces we have are air resistance and gravity. Gravity is pulling down and air resistance is opposing that by pushing up. Again, we have to pick our frame of reference, and it's got to be an inertial one. We're going to attach it to the ground, but the thing is we're going to make the y-axis point downward, so the y-axis will be down positive. So gravity will be a positive force, air resistance will be a negative force, and up is negative. Now we need to apply the equations of motion, and to the ball in the x direction there are no forces. In the y direction we have gravity, which is in the positive direction, minus the air resistance equals mass times acceleration. And again, acceleration will be the derivative of the velocity. Air resistance is the only force we need to specify here, and again, that's just minus kV following Stokes' law. So we collect that together, and we have mg minus kV equals m times the derivative of the velocity. Just like before, we're going to collect all the like terms together, and the difference is now we have mg minus kV. So we're going to divide both sides of the equation by that to get the velocity together with the dv, and we're going to leave the dt on the other side of the equation. Then we're just going to do a little bit of algebra, and this is going to not make sense right now, but later on it'll look like it makes a little more sense, because what I really want is the velocity all by itself. So we're just going to take basically and factor out this term, the minus k over m. So what we have on the other side is just dv divided by v all by itself minus mg over k. This will just make the mathematics a little more convenient. But this equation and that equation are perfectly equivalent. We just rearrange the terms by doing a little bit of algebra. Once we have it in this form, which looks similar to what we had before, because we had the minus k over m times dt, before we just had dv over v, and now we have something that's very similar. It's just dv divided by v minus a constant. So we're going to again integrate both sides of the equation, and we're integrating from t equal to 0. Now at this point the velocity was 0. Before we had some non-zero velocity. Now we're dropping it from rest, so at t equal to 0 the velocity is 0. At some later time t the velocity is some later value v, and this is what we want to solve for. Again, v as a function of t. And again we have two integrals to perform. This integral is exactly the same as it was before, so this integral again is minus k over m times t. Now we have to evaluate this integral, which is a little more complicated than it was before. So here's the second integral. The way we're going to evaluate this is using substitution, because we almost have dv over v, but not quite. So instead I'm going to call this function on the bottom right here u, and then du is just the differential of this, but this is a constant term, it has no differential, so du will equal dv. So we can then substitute that, and we'll have the integral of du over u. But once I change my variable of integration from v to u, I have to change my limits to now correspond to the values that u takes on. So when v equals 0, u is minus mg over k, and when v takes on some later value v, u will be v minus mg over k. So this integral, now using the new variable of integration, is du over u, and my limits are now more complicated. So what I've done is taken the complications out of the integrand and put them into the limits. So the limits are now v minus mg over k and minus mg over k. But this integral right here is now very straightforward. It's just a logarithm. So it's the logarithm of u evaluated at these two limits. And technically it's the logarithm of this minus the logarithm of that. But that is just the ratio of the logarithm of the ratio. So it's a logarithm of v minus mg over k, which is the upper limit, divided by minus mg over k, which is the lower limit. Now we have all these minus signs here, so I'm just going to multiply by minus 1 over minus 1, which simply gets rid of some of the minus signs. So now we have this expression. Now we can set the two sides equal to each other. This is the first integral, this is the second integral. And like before, we're going to exponentiate both sides. So we get e to the minus km over t. When I do e to the logarithm, both of those functions go away because I have the function and its inverse. So that's just mg over k minus v divided by mg over k. Now we just have a little bit of algebra to rearrange these terms to solve it for v. So v ends up equaling mg over k times 1 minus e to the minus k over m times t. So this is our first answer. This is the velocity as a function of time right here. Now, we take the derivative of that, and we'll get the acceleration as a function of time. We find the area under this curve, or do the integral of that function, and we'll get the displacement as a function of time. So if I take the derivative of this, the first term is just a constant, so its derivative is 0. The second term is just a derivative of an exponential, so we take the minus k over m and bring that down. Notice the m's will cancel out, the k's will cancel out. A minus sign here, I have a minus sign there, they cancel out. The only thing that's left is g times, again, the exponential, e to the minus k over m times t. Now notice the acceleration is positive now, and that's because we call down to be positive, and the acceleration, the ball will be accelerating while going down, and we call that positive, which is why I don't have a minus sign here. Then we do this integral right here to get the displacement. It's the integral of the velocity, and we're going to integrate again from t equals 0 to t. The first term right here is a constant, so the integral of just dt is t. So this right here is the first term. And the second term is similar to what we did before, only the constant in front of it is different, because before that was just v0. Now it's mg over k0, over k. And this is now our displacement as a function of time. And I'll leave that algebra for you to work on. So here we have our velocity as a function of time is this expression. Our acceleration as a function of time is that. And our position is this right here. Now we need to check our answers to ask, okay, when the t equals 0, what is my velocity? Well, I plug 0 into here, I get 1 minus 1, that's 0. So my initial velocity should be 0, and it is. I let the t go to infinity, and this term right here will become vanishingly small, and my velocity will approach mg over k, which is my terminal velocity. Now that should make sense because the velocity will terminate or stop accelerating when the net force is 0. When the net force is 0, then the air resistance equals the weight. I solve this for the velocity, and it's mg over k, which is exactly what I have right here. That is the velocity at which air resistance equals weight, and that's my terminal velocity. The units of mg over k are units of velocity because mg has units of weight, or newtons. K will have units of force divided by speed, and when I take this ratio, I get, in fact, units of velocity, meters per second. So this has the correct units. The acceleration, at t equal to 0, the acceleration is, in fact, g. So when it's first dropped, it will be accelerating in free fall. As t goes to infinity, the acceleration will go to 0, which it should, because as t gets large, the velocity does go to a constant terminal velocity, and the acceleration should go away. The position is a bit more complicated, but if we set t equal to 0, the first term is 0, and the second term I have 1 minus 1, which is 0. So at t equal to 0, x is equal to 0. We started at the origin. Now as t gets very big, this term right here will become very small, and the second term will just be a constant. So as t gets very large, this term just becomes a constant, and the position just increases linearly with time. And that should make sense because at this point, the object will be in reaching its terminal velocity, and the position will just increase linearly with the velocity. And that's what this will look like. So if we draw the graphs of velocity, acceleration, and position, we find the velocity will in fact approach a limiting value, or the terminal velocity. The acceleration starts at 9.8 and decreases exponentially to 0, because when the acceleration is 0, the velocity is constant. The position starts out curved when the object is in fact accelerating, but ends up approaching a straight line whose slope will be the terminal velocity. And that's exactly what we would expect. So again, what we have derived here is a new set of kinematics under the assumption we have two forces acting on the object, a constant force of gravity and a variable force of air resistance. And this is what we're looking for, and we're done.